Hello to everyone. We start today's lecture number 2 in our course called Category Theory and its Application. So today we will finish what we started last time. Precisely, we will talk first just a little bit about what is a 2 category, as we will be working with a 2 category of small categories, and then we need to cover a lot of usual material that everybody usually knows up to now, but still we should be on the same page. So we need to talk about what is a faithful function, what is a full function, what is Yoneda embedding, Yoneda lemma, its corollaries, and comma categories. Oh, you are laughing what I am doing, I'm breaking the chalk. Otherwise it's too big to be in my hand. But I like it too much. So first we are going to 2 categories. I will tell you why. Okay, so lecture 2. Today we will be talking about mostly commas and Yoneda embeddings. So last time we have categories. Functors F, G, from A to B. What we had natural transformations. Natural transformations, let's call it alpha G, where F and G work from A forward. We know that we have vertical composition and we have horizontal composition. Vertical composition. We have, for instance, F. Here we have G. Here we have H. With our alpha, here our beta. The same from F. Going beta F. That's horizontal. Going the other way. If we have 2 functors, 1, 2, G1, G2. Here we have alpha, here we have gamma. Then we can make a geometric between F2, F1 and G2, G1. And this will be called gamma star alpha. So horizontal composition. This we already know. All the things we would like to gather in the whole picture. Here I will also write our categories. That factors do not exist in a vacuum. They are arrows between categories. And together it all is in one picture. We want to notice the following thing. Remark. And the functors. First, functions from small A category B form category of functors from A to B, which is called whose objects are F, G from A to B, and so on. And morphisms are natural transformations. The composition is given by vertical one. So suppose we have F G2, which is beta. Here is beta alpha. So composition is assigned to be vertical one. Identity. What will be identity? It will be identical natural transformation. We never talked about four identities in our categories last time, but also always you should think about what our identity, because you can think about some objects that can be multiplied, but what if there is no identity? This happens, but not in this case. So identities, they are natural transformations from F. And let them call. Now I'm thinking how to call them. Let me do one sum of. I wrote bold one. Somebody will write ID as identical natural transformation. It's up to taste of the one who talks about it. Okay. To my Zoom audience, I would like to ask, can you hear me well, or should I speak louder? Because for me, it's very comfortable to speak louder too. So give me please feedback.
I hear you fine.
Yeah.
Great, thank you.
I can hear it too.
Thank you for collaboration. So the second part is. Yes, about this we will talk right now. So we have the functor category. Functors, we are starting from a small category A. Why? Because when we'll be talking about morphisms, so natural transformations, there can happen to be more than a set of morphisms if we are starting from a big category A. I mean big, not small category. That's correct, because big category is a category where there is no assumption on home set at all. So it can happen if A and B are arbitrary, that is the set of morphism between two given functors can be more than a set. It can be a class. So we need this need A to be small. However, if A is small, then this is a category. But A can be a little different, and there will be still a set, and they can be not necessarily one of them small, especially A. Okay, so there is this condition allows us to talk about this, but so it's sufficient but not necessary.
You mean to say that the bacteria will be locally small?
Then it will be locally small. Yes. So if small, I will remind to everyone the small category is a category whose objects form a set. If A is small, then B is locally small. But not necessarily converse. So if this can happen, it can happen, depends. Part 3 of the remark. So consider F category. Category cat. So we love cats. Cats are categories. So who are the objects called? Small categories. Then by the previous remark, one. Morphism. Morphism sets, crossing out the word sets. We are crossing it out. They are factor categories from A to B. The main word here is categories. Composition. What will be the composition? So suppose you have factor from A to B, factor from B to C.
This was
We compose factors. Composition is composition of factors. Applying one after another. Why I emphasize on this? We have up to now 3 compositions: composition of factors, vertical composition, and horizontal composition. Too many things to be composed with. So this is a composition of factors. Moreover, in the factor category, we have itself objects are factors, then morphisms are natural transformations, and composition is a vertical composition. Okay. Then let's call our objects who are small categories 0 cells. I'm trying to introduce simplicial structure. So simplicial complex, they're taking 0 cells, then 1 cells, then 2 cells, etc. Functions. So objects of morphism. Morphism objects are 1 cell, and natural transformations are 2 cells. Yes.
Are you like, does it stop there, or do you keep going?
I can keep going if I will have 2 natural transformations. Okay, so I'm right now trying to get to a 2 category from a category. Right? Once I will get from 1 category to 2 category, in 2 category I can make another step and make a 3 category, and there I will need horizontal composition. Not early. Okay, not early. Because right now vertical composition is a composition inside this function categories. Horizontal composition in this way, if we will follow the following the upcoming definition of 2 category, horizontal composition in the category will be composition of functors. So in our category we have 0 cells, and we have 2 cells. So we can compose 0 cells, 1 cells here using horizontal composition, but we can compose two cells using the vertical composition. Okay. Then after this, we can think about composing natural transforming with a functor that we called whiskering last time, which is precisely horizontal composition with a functor with identical natural transformation. And so on. So right now you get the flavor that somewhere we are around very interesting notion. This notion is the notion of okay. So, not to miss any detail, I will say that. Finish. A two category A consists of class of objects, nothing new. For every pair of x, y, morphisms from x to y form a category, a small category. Third, this is a so-called horizontal composition. Which tells us that for any triple y belonging to A, there exists functor, so C A y to Z, A x y A to Z, U x y Z. This is a functor. Third, not third, fourth. For every x in category A, there is a functor trivial category, one object and one morphism. That I will category of, sorry. In my notes, category C, I'm trying to keep stand with A, B, C, so on. So I'm starting with A. For any set of endomorphisms, let's call it this way, endomorphic object, we have a function from trivial category to this category that picks up a unique arrow, and this arrow is identical function on category X, if you be thinking in the terms of small category cat. And they subject to three conditions, or two, if you want. So, what it is? We need to have the associativity. Associativity looks, how does it look? We have three arrows from X to Y, from Y to Z, from Z to W, and we should compose them in different way. So we are again starting thinking only functorial. So without any choices, belongs, doesn't belong, and so on. So we are taking 3 home sets.
What X is a
Home
function?
category. See?
So that one sub X is a function.
Yes, because this is a category and objects are categories. So objects of morphisms are categories. So the difference between the usual category and 2 category is that it's homes are not sets, but objects of another category, category cat. That's it. So for associativity, we are taking factors from X to Y, factors from Y to Z, and factors from to W. Then there are 2 ways how to compose them. In one way, let's take first category the same, so A from Z to W. And here we compose, so it will be from X to Z. So we will have identity function on a category of on a category which is home object of morphism from Z to W. So first component is stable, we are taking 1. Then we are taking cross with who? With mu X by Z. It's a product of functions. This is a category, this is a category, this is a category. This is a category, and this is a category too. Between categories, we have factors. One factor is mu, which is our horizontal composition. And we are taking the identity factor on this category, A from Z to W, and taking product of factors, which takes first component to first component, second component to the second component. But here we will think of this as a domain of our mu horizontal component, and it lets the. If you know how to write the law of a group law with associativity, identical inverse in form of diagram, this is the same. So who is doing G sets, H spaces in topology, and so on. Here is the same. I'm just categorizing the notion of associativity without elements. I'm telling the order of actions. Here I'm taking triple. This arrow composes first 2 elements in a triple, or no, second to it. I will follow this way. This arrow will compose this pair, so it will be A from Y to W, A from X to Y, and here will be compositions, just pure compositions. So here I will write mu Y dW cross identity factor. Here will be mu XYW. And here will be mu XZW. Right now I'm doing very baby thing. I'm writing all the indices. Serious stuff, guys. Never write these indexes. This is like understood. Okay. So right now we are in a sandbox in kindergarten, and we are playing just with this definition. Later, of course, you will see if I will be writing all this X, Y, Z. We'll finish the lecture there. So when I will be giving the definition of bicategory and so on. No, there will be still indices, but more I will deeper I will be going, harder it will get to follow everything so precisely. But don't forget to be very precise when you are programming, when you will be trying to make some program that will be composing something with the sum. if you will be skipping the steps and in understanding who is from where, then you will enter the world of pain. Well, and another axiom. Axiom tells us that the composition of this identity should be trivial. So let's think in the following way. I'm taking category of morphisms from X to Y, writing that is the same as category of morphisms from X to Y cross trivial category. So adding a fake component to every object doesn't change anything. So it's one dot with one arrow in it. So we can just add a fake label to every object and to every arrow, nothing changed. Then write the arrow down. A. So I'm here identity cross identity sub X. This is our identity sub X function. I know too many identities, but I'm also being confused sometimes. But looking at the arrow, you have no other choice what to do. So this from 0 to here, what should be on the left? Then we are taking composition. Here will be mu x, x, y. And this is an identity arrow. So the thing tells you precisely that multiplication with an identity arrow, identity on a domain of your morphism, is trivial. In other way, let's practice. Sandbox is for practice. How people will call this morphism? They will write mu. Here will be blank, and here will be 1 sub x. And this one. The factor. So the composition of these two factors you usually see in this way. Okay. This will be mu. 1 sub 1 comma blank. Soon we will encounter 4 factors. And there you will understand that in the pi function, we can twist components and get something similar to home, but not precisely home. So that's our last condition. That's it. What I need also to tell, it's about terminology. So the objects of two categories are called zero cells. The objects of category of morphism from X to Y called 1 cells. Then arrows here are called 2 cells. And composition is called vertical composition. It can be checked. I'm emphasizing it can be checked that in two categories the law of Miller-for exchange, so how to combine horizontal and vertical composition, works. Why it works? Because it works for functors and natural transformation. So we are referring to this, to cat. We are referring to cat. So we don't need to get it from outside and say, and this law is assumed to be true. I'll remind that this means that, let's write it in a way of box. It's as in homotopy theory. You have it so alpha, gamma, delta, alpha, beta, gamma, delta, alpha, gamma, beta, delta. This works vertical composition, here vertical, here horizontal, here horizontal. Between two ready-made vertical will be here horizontal. And here will be just vertical. And it doesn't matter how to do this. Why? Because we can prove this for functors. And our all arrows are functors and natural transformation. So 1 cells and 2 cells. And this works this way. Okay? Now I want just to tell a little more about some appetizer for the future, that in the case when this triangle will be commutative, not triangle. Well, it should be triangle because I was very precise when I wrote this isomorphism. It's just for the first time. Usually this isomorphism is never told. What is it? It's just written from xy to here. This isomorphism is assumed to be present there. But to be super careful, we should write. And therefore it will get as a triangle. So in this triangle, and in this rectangle, if we have not equality, but natural transformations, and here it will be, doesn't matter, by the way, where. Natural transformations, that are isomorphisms, natural isomorphisms. And they work in some specifically good way, then we will have bi-category. What is a specific way? They are coherent. There are certain pentagon axioms and so on. So when we are allowing ourselves a little to weaken the necessity of f by 1 is f, 1 by f is f, f, g, h compose how much you want, so it's not equal but isomorphic, you are getting bi-category. For this reason, two categories are also called strict two categories. And weak two categories are called bi-categories. Let's write this down. I mean, I'm trying to give you a hint in terminology, as once you start reading something more serious, even looking through internet and Wikipedia and so on, you're just thinking, well, bi-category, is it a name by other school for two categories? No. Once as I remember it was, but this terminology in 50 years, changed and so on. But so right now, nowadays, we have two categories. They can have to be strong and weak. So strong, we call just two categories. And weak, we call bi-categories. Strong means that associativity and identity are equal. Here, associativity and identities are isomorphisms. Then, following this way, we will have two functors, natural transformation, and so on. In this way, we will have pseudo function, pseudo natural transformation. That's it. When you are assuming that your function keeps composition up to coherent isomorphism. When your natural transformation gives you that hexagon that I was writing the last time up to coherent natural isomorphism. That's it. Okay, I spent so much time on something that I was going to spend like 10 minutes. But I hope this deep insight in higher category theory will help you a little in the future. Right now we are going to our stuff.
Alex, you wrote that the set of the collection of morphisms from X to Y is a category. Do you mean that it's a small category?
Small. That's what I wrote before. It's a category of small categories, cat from small. I mean, cat where A and T are small.
In the case when big, that was the functor category. Like sometimes we don't have that the functor category is small, right?
Yes. I mean, so this thing should be a small category. This thing.
Yes.
Yeah. And functor category will be. Wait. Good question.
Because the functor category might not be small, right?
Oh yeah, it's locally small when it's small. Its objects are factors, so we need two factors to constitute a set. And okay, right. So if you have both x and y are small, then the factors are picked up among the functions between sets of objects. So if this is small and this is small, factor from x to y is a function from set x to set y, such that and some additional things for how to work with morphisms. But they are already, picked up from a set, and subset of a set is a set, it's not a class. Fantastic question. You can give yourself a credit. Even 2 credits. Okay. On each show. So, yes, when they are small, the function categories are also small. So small, smaller. Okay. Examples of 2 categories. It's a category of small categories. Okay. It's the first example and the one that we will need. It's a strict category because other 2 will be usually byte. Actually, for instance, profounders. Okay.
So strict and strong and synonyms, we're using them in the same way.
Yeah, well, strict or strong. It's not a native speaker, right? Strict. Thank you for. You can also have a credit, but only one. For the credit, you need to work hard. Good. Then part 2 of today's lecture, it will be something very small. Let's call it representable functions. Representable functions. We have A category, object A, B, belong to A. This is a fixed stuff. Then definition. Functor, which we will write comma blank. From category A to category of sets, that every object X takes to the set of morphisms. Let's write down this way. Also, is A as an index. Okay, here. Later we will be omitting where it's understood, or using Einstein notation. Every object goes to a set of morphisms from A to this object, and every arrow from X to Y goes to a function from set of morphisms from A to X to set of morphisms from A to Y. Is F. Here we will also call it A comma F, or just F lower star. How does it work? So A comma F goes from A Y in the following way. When we have an arrow from A to X, it's an arrow G. Then this arrow goes to composition A to X, from X to Y. Here is G, here is F, here is F. Or shorter, that F over star G. The thing is that is not usually written, but if you think a little, physics, mechanics is the following. You have some sets of strings from A to X. That is strings, not string theory. I mean just regular strings. Okay. I know there are a lot of people who will try to make assumptions. No. Then this is an angle of turning. So we all move them, just attach an X to Y, and every string from A to X gets a string A to X and to Y, so from A to Y. I think it's about angle of. When your beginning is fixed. Okay. Until this. Or just when you have a function. Function F. You can change here what to do something like this. Excuse me, here not G. And then get a new one like this, right? Why it's the same here. So you are changing the domain of a function. But we needed codomain. No. So we should think in the following way. Yes, that we have arrow G from A to X. So you are changing the codomain of a function. Before what I wrote, it's also fine, but it's for other cases. Such functor will be also called often covariant representable. variant representable factor. X is representing object. Other notations. For it are A comma blank when the category is understood. H superscript A. We're using for first argument superscript, for second argument subscript. It's in old books usually. And the one that I will be using soon, it is this. Because home set, I will be writing as A, superscript A, lower script B, X, Y, so on. So this is more my notation, but this notation will be consistent with the theory of property, as they will generalize all this situation. Other definition. We have fixed the covariant argument. What will happen if you fix the contravariant argument we fix? What will happen if you fix covariant argument? Then we will get a contravariant representable function. So a function A blank comma B category A op, because it will be acting from it will be putting argument on a contravariant spot. And all functors that we are talking about, usually we are trying to make them covariant. It's a contravariant, we are putting op either on a domain of a functor or on a codomain of a functor. Or just write from domain to codomain as it is, and then emphasize that it's contravariant. Composition of two contravariant functors is what functor?
Oh, covariant.
Covariant. It's like minus by minus gives plus. So contravariant functors are fine to write, but when you compose them, unfortunately, happens something not nice. Here X goes from A from X to B, arrow from F from X to Y, goes to an arrow from A to B. Stop. We should here have X op, X op, F op, Y op. So this is the same as arrow F from Y to X. So then we will have from AX. Here will be F upper star, A F comma B. How does it work? So our F upper star acting on G acts as a recomposition. That is possible. Or composing here on the right, there on the left. Using this comparison, here F lower star changes codomain, lower star corresponds to codomain, F upper star changes the domain. So it was function from X to B, it gets function from Y to B. And as you see, if we, for some reason, we're not careful, and right here, arrow that we had initially from X to Y We write here arrow from x to b, here from x to y. And what? We can do nothing with it. We will just have a roof. There, it's a roof. We don't know what to do with that. But when we have from x to y, yeah, we can compare. That's what we can do. Then A is a contravariant. Other notations is like comma b, a over b, and a over b. Representable functors play the same role as free modules or projective modules in module theory. They play the role of building blocks of which everything is trying to be gathered. And most of the notions that we will be working with will get this or other way to the determination how to approximate our situation or represent it with a covariant or contravariant representable function. Everything what will be doing. Some situation will generalize have both ways. It depends. So representative functions are the best functions to work in. If you have a category, you don't know what functors are going from at the beginning. But I mean, you of course know to the trivial category, just collapsing everything. To itself identities, that's fine. But to other categories, how to work with them, you don't really know immediately. But you always have something as a space of functionals in functional analysis on your space. So functions from your normal space to R or C, or whatever you are taking the field. So here we have functors that are from your category to the place of your relief, to your paradise, to your cosmos set. Precisely set is a cosmos, but about cosmoi we will talk a little later. So always you can build from any category so many representable covariant and contravariant functors, how much you have objects there. So you have immediately plenty of functors, and they're all different. Okay, now small part 3 are, it's just baby stuff, but I need to state it, it's types of models. And functors. Okay. Is a monomorphism if it is cancelable on the left. Morphism. It's cancelable on the right. First means that if f g1 f g2 follows that g1 g2 situation A and B if g1 f equals g2 f, then take f R S equals identity, automorphisms. Then R is defined to be retraction, and S is defined to be a section. So sections and the retractions always go in pair of morphisms that are composable to identical morphisms. In this pair, left divisor is a retraction, right divisor is a section. D. G equals G F equals. I can write this. We are not in kindergarten because we will have different domains, codomains. One. Then F is isomorphism and inverse F minus 1 is defined to be G. Of course, since R is defined, it's unique, and so on and so forth. Everything that you know from group theory. Why I wrote separately? Because F here, G here, X, Y, X. So GF will be 1 sub X. Here will be 1 sub I. I can't write FG equals GF equals 1. It's in groups, you can write. No, not as a way. Okay. Then I won't be myself if I won't type the previous talk and the current. So let's tie together representable functors and types of morphisms. So, statement. F is mono. If and only if for every and in category A and comma F is injective. It's an injective function. What is it? Lower step. How it acts? By multiplication on the left. So if you have that it's injective, then having equal images by multiplication on the left, you will get equal three images. So it's mono. It's happy if where the A, let's call B, belonging to A, upper star A, F, comma B, is injective. If somebody wanted to write surjective function, you will get different things. Funny, but true. So the notions that are seem to be dual will give us passing to the universe of sets both surjective functions. The reason is the same. F upper star is multiplication on the right. If multiplication on the right gives the same result, then the preimages were the same. So it's exactly. I was lazy. Did not write that it's mono, it's F. Then F is a section. Okay, F is a section if for every B belongs to A, F star B is surjective. reflection. Subjection function. What's the problem with being subjective? Is that we can take what we need, domain or codomain, in it pick up identity and lift it up by surjectivity. So surjectivity allows us to lift identities to find the preimage of identity when we multiply on the right or on the left. Well, that's it. Sad but true. That are from A is a natural isomorphism natural sort of transformation from F to G is a natural isomorphism if for every X into A, alpha sub X is an isomorphism. In this case, F and G are isomorphic. So isomorphic functors are functors between which you can find a natural isomorphism or natural transformation whose components are isomorphic. Okay, then next. Categories A and B are isomorphic if there are functors F from A to B, G from A to B, such that GF is identity functor on category A, FG is identity functor on category B. Let's put here lower Roman 1. Categories A and B are first isomorphic, second equivalent. GF is isomorphic to 1 sub A, FG is isomorphic to 1 sub B. Remark. I will just tell the remark and you can write it down. By the usual convention in category theory, we are only looking for equivalent categories. We are never looking for isomorphic. Because to get exactly identity functor, it's a super rare situation. It happens. When? I will tell you first. But to get it, I think you should have a very specific category.
This is kind of like a categorical version of like homeomorphic versus homotopic equivalent.
No, it's homomorphic. I mean, no, yes. Homotopy, kind of. That's right. Because for homomorphism, we are requiring the inverse. So the bijection. Here we do not have a bijection. We have here f minus 1. Weak inverse. If you'll be reading some literature, there you will find that it's weak inverse. Here it will be inverse. So we are looking for a weak inverse, being more precise. Okay, now to finish this baby thing, definition. Function. F is faithful. 1L, as I remember, right? Who is native speaker? If components of a function on morphism sets are injective functions, F is full. The surjective. Fully faithful. Bijective. B. F is essentially surjective for surjective on objects. For every B belonging to category B, there exists A belonging to category A, such that F of A will be isomorphic equal that every object has a preimage.
Up to isomorphism, right?
I mean, pick up, if you have, pick up other one that will be, you don't need, if you, here you would have an isomorphism.
Yeah, I mean, this means for any object in the target category.
There is a preimage.
Not exactly, right? There is.
So there are other definitions where it's isomorphism.
Yeah, I think that's why you don't say subjective, right? That's why you say essentially subjective.
Ah, really? Because you always where I was looking for essential subjective, always was just this.
But I think that would be like a definition for a dense functor. A dense functor. It's when we put the isomorphism.
Yeah, I mean, it's the same thing. Dense and essentially subjective
Okay.
are interchangeable.
Okay.
So here I should put isomorphism. Okay. Dense and co-dense will be way. If there will be, because I have so much things to do with you and so little time. So So much things to do, so little time, so little time, so much things to do. Theorem. F from A to B. As a weak inverse. If and only if F is fully faithful plus project. So categories are isomorphic. Actually, categories are equivalent if between them you can find a functor that is fully faithful and essentially surject. Also, fully faithful functor will be sometimes called embedding. As you take your category and it has a copy inside the other category. That's embedded. Really copy. That all home sets are the same. All objects that goes one to another, you know, like a tile from a whole tile set. Good. Definition. A subcategory prime of S category A is a category with of A prime laying inside of A in classes and A prime between X and Y lays inside A between X and Y. It's 1, 2, 3, and compositions agree. And compositions agree. Definition. A prime is full category. A prime in A is a full functor. So we don't require that they get to be equal. So it's not embedding, it's a full function. Category A is a skeleton. Yeah, we start in biology. And underline, simplify and define. If from the fact that X isomorphic Y in A follows that X necessarily equal Y. So the category does not have isomorphic object. And then every category has a category which is skeleton. Second, every category is equivalent to its skeleton. That's it. How do we do this?
But like maybe this is a stupid question, but so like I would.
There are no stupid questions, there are stupid answers.
So I guess skeleton is unique up to something. Like
All skeletons are isomorphic.
isomorphic.
Wait, isomorphic or equivalent? All skeletons are equivalent.
Oh, no, nice.
But if you are considering function from a skeleton to category, from category to skeleton, it will be exactly identical because there are no isomorphic objects. But if you consider function from a category to its skeleton, from skeleton to its category, it won't. It will be just equivalence of functions. So skeleton, you can think as a deformation retract.
Skeletons would be isomorphic, right? Skeletons would be actually isomorphic, right?
Wait, let me think.
Because you say
Yes, skeletons will be will happen to be isomorphic. Yes, it's another step, right? They're not only equivalent but isomorphic. Yes, not the same, but isomorphic. Yes.
And in the first statement there, do you mean to say every category has a full subcategory which is a skeleton? Or
I never said the full.
but I
I
was
need
under the
to-
impression you
I need to think, is it full or not?
okay. Because I was under the impression you require a skeleton subcategory to be a full subcategory which
I am requiring the category to be a skeleton. If this subcategory is a skeletal subcategory, if it's as a skeleton as a category.
Is there a canonical way to get, there should be a canonical way to get the skeleton, right? You mod out by, you somehow make all isomorphisms equivalent or something?
No, unfortunately, no. So you're, Jeremy, you're picking up as from every set of isomorphic objects, one object, and you are getting it to category. So that's first, it's not canonical, you are making a choice. Second of all, to every object, you are picking up an isomorphism with the other objects of its class of isomorphic objects. You don't need this choice for constructing your category skeleton, but then you will need this choice for this defined picked up isomorphism between isomorphic objects from your skeletal object to define an inverse. To define an inverse of, so from category A to, I will tell you precisely how it goes. So if you have a morphism from A to B, okay, then from A, you need to take an isomorphism to A prime in skeleton. From B, you are taking an isomorphism from object in skeleton. And for them, here is F prime. So you are picking up some sets of objects, some morphism between them. And when you are trying to get from a functor, from the whole category to its skeleton, you are, every object you are passing to the representative of its class of isomorphism. And every F goes to this F prime. And how? Just composing or repost composing with this invertible morphism. So that's how you go from one to another. But there is no canonical way, as you can pick up many ways. So two objects can be isomorphic, I don't know, probably in many ways. As even for one object, the set of automorphisms is not necessarily of one identity, right? You can have more, but you are fixing them to get an isomorphism between, to get an equivalence. And you can pick up different representing A primes in the same class of A. So I won't say that it's canonical, because canonical for me is the one that does not depend on the choice. Here it depends on
Yeah,
the choice.
you're right. You're right.
Thank you for your question and that you are here. I know that I am being listened by my remote audience. Good.
Right, but for this second item, when you write that, you need that this capital is full, right?
Otherwise, it can't work, right?
Like your definition for the first one?
Yes, but it will follow. Okay, it will follow from the fact that I can build and
But then we say to its skeleton, you need.
it will so from equivalence, or not equivalence from the fact that composition of two functors is isomorphic to identity follows that one of them is full, one is faithful. Bijection. One is this, one is that. So yes, it will follow that it's full subcategory.
Again, like a not stupid question, but like feels-
No stupid questions, stupid answers.
So like, okay, suppose that you have a category with just two objects,
Great.
right? And so wouldn't the subcategory with just one of those objects be a skeleton by this?
Are these objects two objects isomorphic?
Let's say they're not.
Then no. You are in a.
You have one object per isomorphism class of per isomorphism class of the
So you're breaking your whole category.
if each of is isomorphic, you just treat and just pretend as one object.
You're breaking your category in a class of isomorphic objects. As you're doing with cosets when you're taking quotient group.
But in other words, so like, but that definition there seems to suggest that we just have to have, right, so a category is a skeleton if they're isomorphic whenever they're equal, right?
So things are isomorphic. Okay, well, yes.
So in other words, if I had the subcategory that just has one thing in it, right? And
Okay, give me your category. So it has one object or two.
so let's say that there's like one category with two objects. And then there's a subcategory with just one of them. Right? And yeah, right. And so and the two objects are not isomorphic. Right. So according to that definition, am I wrong that the subcategory would be a skeleton?
The subcategory is a skeleton.
Right, but that's not what you want.
Yeah, but that's not what we want. That's what is strings.
The fullness is not the issue with that example, though. The issue is that you need for every isomorphism class, you need at least one object. So some sort of maximal skeleton. It's not the fullness that's the problem. It's the maximum condition.
So every category has a full subcategory, which is a skeleton. Right. I think this will solve this thing. Right, Jeremy. Thank you. Yes, so it can have subskeleton, a subcategory with skeleton is again a skeleton. But we need the one that spans.
But
Yeah, right. We should require it to contain.
I think you should just change the category to skeleton.
Yes, it's how, but it's a construction, how it gets. So there is a construction and there is a statement. Here I'm trying to get a statement, but the statement is realized by a proof, and the proof has this construction. Exactly what you're telling. That's right, from every isomorphism, yes.
but you also.
Yeah, but then two doesn't follow, right? Because then it's not equivalent to its skeleton. So like this skeleton should be its full subcategory skeleton, right? It's in number two, because this is an example where it's not equivalent to that skeleton that you've made. So it should be equivalent to
But because like here the skeleton should be this.
the full skeleton, right? What, you know what I mean?
Mhm.
Because the example he made is a skeleton, but it's not equivalent.
So,
Two doesn't follow.
Good. So how?
So the inclusion has to be dense, right? The inclusion of the subcategory has to be dense, right?
Yes. So let's then say that's what essentially subjective. I'm sorry.
Well, every category is equivalent to a skeleton that's a full subcategory of it, or something like this. If you're full, then it you
So every category is equivalent to its full subcategory, which is a skeleton.
something like this.
No, because
That's
when you
the
just
whole
take one object there for the subcategory, it's still full. Because you can take 5.
Yeah, that's again what I was saying is that the fullness is not the issue, because if you just delete everything but one object and you look at its endomorphisms, that will be full, right? Like it's more than just the fullness.
Well, let's think about this.
So think about
Yeah,
this.
so that's what I was saying. So I think what ideally is done is you require, you make sense of a skeletal subcategory of a category as a full subcategory, which contains at least one isomorphism class of each object of the parent category. So that this issue.
Not at least, but exactly one.
Yeah, exactly
Right,
one.
right, right.
And then you say that every category has a skeletal subcategory.
What you're telling is precisely right, and it's a proof.
No, I'm not telling you the construction at all. I'm just saying.
Its existence. You are telling how to prove the existence. That will be. But how to formulate precise state? Okay, let's know. And next time I will think a little more, because we have also other things. But thank you for good point. I need to think more about it. I was thinking yesterday, but you see, I have stupid answer. So finally,
Every category is equivalent to its skeleton.
but what we mean by its skeleton?
Okay.
That was the question.
But I said
To ask us.
Max
Any
skeleton.
skeleton.
Yes, but any maximal skeleton.
No, but you can say every category is equivalent to a skeleton, and then that does it, right?
It's not very much. Yeah, sure, yeah.
Okay, so from this symmetry full of skeletons, we should a little go deeper. Well, finally, we finished what we were supposed to do last time. I'm shocked. Today stuff. So again, we are almost done finishing. So you have.
Oh no, that was just last week.
Okay. How much time do we have? I mean, the remote audience can finish with us or watch later. How much time? Who has? Do we have half hour more? Like 40 minutes? How much? How much you want to say? Maybe people have office hours and so on. No, not till the evening.
I have 10 minutes. 20 minutes from
20 minutes.
Yeah.
Okay, let's try to do 20 around. So. You scared him. Good job. Part 4. Yoneda lemma. Yoneda's lemma. I'm forgetting.
That's right, yeah.
Once my advisor explained to me when you're putting sin of someone, so of someone, or without it, but I forgot. So Yoneda lemma. And A belongs to A. It's an object. It's called part A. Then natural transformations between functors A F are in a bijection with a set element of F of A. Usually here in book you will see natural transformation of these functors, but now we know that natural transformations are home sets of a functor category. We have two functors from category A to category Z. First one representable, second one given, and then natural transformations from one to another First of all, well, right now we don't have any assumption of category A, basically. So that's a class from one side. So we are stating that this class is in bijective correspondence with a set f of A. This is a set. Therefore, this is a set. Exclamation mark. Before it was a class, but it gets to happen. How to prove that class is a set in this case? You are taking the class, then taking a function from a class somewhere to your set, and proving that it has inverse. When you have bijection between class and sets, your class is actually a set. So the thing in this theorem that it's constructed. It tells you how to construct the isomorphism of bijection in category of sets. It's not only that it exists and go away. It's not the axiom of choice. Something exists. Get lost. No. Here you need, and you can prescribe how it works.
So the source category, is it required to locally small?
Well, we think that it's locally small. Always think about locally small categories unless it's stated. But some main categories that we will be working with at some point like this. Sometimes we want to state some statement and to be not too much thinking about such theoretical issues, so it can involve bigger categories than locally small. But still, from the isomorphism in can extensions and so on, you will have a flavor of what's going on. So you have isomorphism between classes. Here we are working with locally small categories, and we have isomorphism, so bijection between sets. How it works? So suppose you have a natural transformation alpha on this side, factor to f. Then what we do with it? We are taking its. I'm not solving a couple steps. I'm just giving step by step. Then we are evaluating its component at your given object A. You don't know about anything about your category. It's why it's canonical, because you have no other choice in certain ways. So you always should have the choice to pick up object A. You have no other objects that you know about. Then it gets a function. It gets a function between set of endomorphisms on object A and value of functor of A. And then it goes to the value of our function endomorphism on object A. Conversely, suppose you have object element x belonging to f of a. Then you are sending it into natural transformation. You should have a natural transformation. So this natural transformation, what is it doing? It's picking up on every component a function from A to B, I mean a morphism from A to B, applying functor f to it, I would say twisting it with functor f, and evaluating at x. So the inverse of the function that takes natural transformations to elements of f of a. The inverse is an evaluation of a twisted morphism by functor f on element x. one can check, spend his spare time, check that this is actually an isomorphism. What I forgot to say, that this isomorphism is natural isomorphism. What's happening? So you have morphism f from A to A prime. Then to it you're applying a function. You will get morphism in opposite direction. So think about blanket sum x. So you apply contravariant factor a something x, but instead of x we have now blanket. Then you are again applying representable factor with a representation f, but it's contravariant, so it's again terms. So this thing is here. What it will be? It will be it takes natural transformation from this thing and composes it with a natural transformation. It's a proper stuff. So it takes natural transformation and composes with this thing. So when applying to every single, etc., etc., etc. Wait, I wrote it wrong. I wrote it in the wrong place. It's here. So it's naturality in A. Naturality in F. You have a natural transformation from F. Like, right? And then you will get there's an arrow here. It's a lower step. With multiplication is xi on the left, if you will be composing. Okay. That's naturality now. corollaries. Corollaries first. A comma blank. B comma blank. Is natural isomorphic to B comma A. Oh, by the way, I wanted to state Yoneda lemma for B. I'll state it here. I mean, it has nothing specific. So blank comma B is morphic to G of B, where G is from A open. So if you have contravariant factor, you don't need to prove anything. You're just changing category A by A open. That's it. And all walls in your representable covariant going to contravariant and so on. 3. Network transformation between two represent covariants of contravariant representable factors corresponds to element. So if here is function f, this function corresponds to blank comma f. Or lower state. So there vice versa. F corresponds to f upper state. Or A is isomorphic to B, but not to be twice right. One of these. Well, if they are isomorphic, then this in this set pick up this isomorphic, it corresponds to isomorphism there. If this isomorphic, then take this isomorphic and it will be brought there. Just gain from the left to the right. Definition. If A is a small category, then we have a category I set category A of. This category is sublocal. This one is called category refuse. Okay, and this co-precious probably. Here, These two functors are embeddings. First one is called covariant unit embedding, second one is called contravariant unit embedding. They theorem is, first of all, these are functors, follows from unit level. Second of all, that they are embedded. So they are fully faithful, can be seen using this, and this facts. Fortunately, I have not enough time for comma categories and category of elements. So, but at least a good chunk of today's we did Yoneda and all around. After we have established the background very well, we can go now to comma categories, then to adjunctions, to universal constructions, and we are done with the basic categories theory. Then we are going to more advanced stuff. I mean, the difference between basic and non-basic is very conditional, depends on who will decide. From somebody can extensions and now just sit and compute. A couple of years ago it was different. And then after the limits, co-limits, what we'll have. Just another thing what's going to be next. After that will be paragraph 5. Oh, I don't know if to do paragraph 5. Maybe tensor compo tensor. No. No. Maybe monoidal category. I'm just so itchy to just give you a monoidal category and tell how many monoidal categories we have. Then we have enrichment and just let's forget it and work only in enriched set. But anyways, we are doing this enriched in set. Thank you for your attention. If you have any questions, you are free to ask, to join anytime. Come to me. I'm every day in my office. Thank you again. Thank you.